Alright, so we're going to talk about special segments. It makes it sound super exciting, as I'm sure you can't wait to hear all about them. Alright, so Theorem 914 specifically states that if two chords intersect, excuse me, in a circle, then the product of the measures of the segments of the chords are equal. So in other words, all this is saying, these secants, which have chords of the circle in them, create one piece, two piece, three pieces, four pieces. So there's 4 pieces cut. And if you multiply this piece times this piece, it equals this piece times this piece. So you put the pieces that belong to the same chord on the same side of the equal sign. So I would have AE times EC is equal to BE times ED. That's all you're going to do. Piece of cake. Alright, so we're going to look at the example below. Now, mind you, I know absolutely nothing about working on a car. That's what my husband's good at. I let him deal with all that stuff. For all I know, some woman wrote this problem and doesn't know what she's talking about, but we'll go from there. A mechanic needs to know the radius of a rotor to find the correct size for a new part for a car. I don't know, perhaps he's putting brakes in the car. Who knows? He doesn't want to take the whole car apart. I think it's not that difficult to find the measurement of what he needs, but we're going to make it into a math problem. However, he can measure only part of the rotor without taking the engine apart. If he... Is an engine really down there where the rotor is? None of you work on cars in here? Any of you know anything about it? Well, good. Oh, you do. Oh, you do. The rotor's by the wheel, isn't it? And the engine wouldn't be anywhere near it, would it? See, I'm thinking a woman wrote this problem. Or a non-knowledgeable guy, right? All right, so we'll just ignore all of that. Tony, ignore all of that. If he measures a segment of 6 inches, and the distance from the midpoint to the arc is 1.5 inches, what is the radius of the rotor? So he was able to measure this part of the rotor all the way across is 6 inches, and this part right there is 1.5. And that's the midpoint to the arc. So what they're implying is that this particular secant or chord goes through the center of the circle, doesn't it? So isn't this a diameter? What does a diameter do when it intersects, bless you, a chord? It makes right angles. What else does it do? It bisects it, doesn't it? So if this whole thing is 6 inches, isn't this 3 and isn't this 3? Because you need to know the 2 separate pieces. The question is, what is the radius of the rotor? Because the 1.5 is not the radius. If I find the whole diameter of the rotor, can't I then cut that in half? In order to find the whole diameter, I have to know this piece, which I'm going to call X, from here to here. This is the unknown piece. So all I'm going to do is use the formula that they gave me. And I'm going to take this piece, 1.5, times this piece. So 1.5 times X equals this piece times this piece, bless you, 3 times 3. So I get 1.5X is equal to 9 divided by 1.5, and then X is equal to, without a calculator, all I have to do is move the decimal 1 place to the right, add a 0, because I'm moving the decimal 1 place to the right up there too. I've got 90 divided by 15. How many times does it go in there? 6 times. So this is 6 inches. So the whole distance from here to here is 6 inches. Does that answer the question? No. So I need to find the diameter. So my diameter would equal 1.5 plus 6 inches, which is 7.5 inches. And then they want the radius, right? So the radius is half of 7.5, which 2 goes into 7 3 times, with 1 left over. 2 goes into 15 7 times, with 1 left over, and 2 goes into 10 5 times. So isn't the radius 3.75 inches? And that's what they're asking for. So therefore, the radius of the rotor is 3.75 inches. So that's easy, right? And remember, you will have your Ames reference sheet. You're not going to have to memorize all these formulas. You just have to know when to use them and where. All right, so part of your picture is cut off here. This is supposed to say external secant segments. That's a tongue twister. Say that 10 times fast. I dare you. All right, so this one says that from S to C, which is part of a secant, and S to A, which is part of a secant. There's segments, so that's why they're called secant segments. And they also contain the chords EC and NA. SE and SN, these are the external portions of these secant segments from here to here. Do not mistake those as tangents. Remember, tangents that meet at an external point outside of the circle are equal. Well, these are not created by tangent segments, so they're not equal necessarily. They could be, but they're not necessarily equal. So these segments, SE and SN, are the parts of the whole secant segments that are external to the circle and are called external secant segments. So what do you do with them? Well, I've got this theorem, and then I'll simplify it for you, make it easier, because even if you try to use your Ames reference sheet, it looks confusing, and I'll just make it super simple for you after we go through the theorem. So if two secant segments are drawn to a circle from an external point, which is what you have above, then the product of the measures of one secant segment and its external secant segment is equal to the product of the measures of the other secant segment and its external secant segment. It's very similar to the one we just did with the internal secant segments. In other words, the ones that are intersecting inside the circle, where you took the products of each of the pieces and multiplied them together and set them equal. So all this is telling you to do, this is exactly what that's referencing above. So SE is the external. You multiply it to its entire secant segment, which is SC. That should be equal to SN, the external part of the other segment, multiplied to its entire secant, SA. So you're going to get a couple of different cases of this, several different cases. All you need to remember is multiply outside to whole equals outside to whole. That's all they're saying. Outside to whole equals outside to whole. Multiplying together. Easiest way to remember it. So we're going to apply that on example 2 below. And this is showing you that GL and EL are definitely not equal, 6 and 8. They're not tangents. But we have to find this chord right here, X. So if I'm going to set up what they just did before, I'm going to take the outside, which is 6. I'm going to multiply it to the whole length of the segment. Is the whole length of that segment 6x, or is it x plus 6? Because you would be adding, right? So x plus 6 outside times whole equals outside of the other secant segment is 8. What's the length of the whole secant segment? 18 plus 8. So for your notes, make sure you put 18 plus 8, because if you put 26 down, you're going to go, well, where did I get 26? I have no idea. So then all you have to do is follow your math. We're going to distribute the 6 inside. Some of these might require factoring, by the way. So you might, if you have an X outside and an X here, anytime there's an X here on the external part of the secant segment, then you're going to end up possibly factoring because you're going to have an X squared. So beware that factoring could come back to haunt you. Again, you should not be using a calculator for tonight's homework. I especially don't want to see decimal answers. So on this one, I know that 2 goes into both 6 and 172, but I know that 6 doesn't, because 1 plus 7 plus 2 is 10, and 10 is not divisible by 3, and that's the other part that divides into 6. So I am going to reduce them by 2. So X turns out to be 86/3. You should not be getting negative numbers for these answers because you can't have negative lengths. So beware of that. Then flip it to the last page. This time we have a tangent with a secant segments. So if a tangent segment and a secant segment are drawn to a circle from an exterior point, then the square, so here's your formula, then the square of the measures of the tangent is equal to the product of the measures of the secant segment and its external secant segment. I don't want you looking at this as if it's a totally new problem. Let me just show you on this picture why it's not a new problem. It's the same problem as before. We just happen to have a tangent and a secant. So remember it's outside times whole equals outside times whole? What's the outside of this tangent segment? CE. So this is outside, right? What's the whole tangent segment? CE. So outside and whole on the tangent are the same. That's why they're saying to square it. But I want you to view it as being no different than the last one that we looked at. Outside times whole equals, outside is DE, times the whole, which is from B to E. It's no different. Don't bother to learn something new. Look at it as if it's exactly the same. All right, so then look at number 3. In the figure below, RT is tangent to circle B. Find the value of X. So here we have X outside the circle. So you might end up factoring, but in this case you won't, because didn't they give you the entire length of SR? They didn't say that that was 16. 16 goes from S all the way to R. You have to be careful and figure out, well, what are they referring to? What does that number refer to which length? Sometimes it's not quite as obvious as you would think. All right, so again, I'm going to go outside times whole equals outside times whole. That's the mantra. So my outside of my tangent is how far? 12. My whole is how far? 12. So those are the same. My outside of my secant segment is what? X, and my whole, in this case, is 16. It is not 16 plus X, because they said that whole distance is 16. So go ahead and solve. 144 equals 16X. Divide by 16. So you get a value of 9 for x. Questions? The only thing that becomes complicated is they just start to put everything together, mix it all up, everything that you've learned in the entire chapter. So just be careful. Have your Ames reference sheet handy when you're doing tonight's homework.